In this video, we'll be looking at 6.1 exponential functions. An exponential function is a function in the form f of x or y equals a times b to the x power. What you'll notice that's different about this type of function is here we have the exponent, the independent variable, our input is in the exponent. We're going to be inputting some x that is up here in the exponent. That's why it's called an exponential function. This a value, a, is a starting value. It's the y-intercept, okay? That is, it will be the point 0, comma a. If we input an x value of 0, well, b to the 0, anything to the 0 is 1, so we're left with 1 times a. If x is 0, the output, f of x, or the y value will be a. This b is a rate. All right? This value of b is going to give us some ideas about the graph. If this b is greater than 0, if b is greater than 0, then we have exponential growth. Graphically, what we'll have is something that looks like this. When this value b is greater than 0, we're going to have exponential growth. What that's going to look like is a curve that is moving upward as we increase xy's, this being our x, this being our y. In this direction, it's going to get closer and closer to our x-axis but never touch. We say it approaches asymptotically. It gets closer and closer and closer but never gets there. That is exponential growth. Looking at a table, it'll look like this, x and y. Let's take, for an example, y is equal to 3 times 2 to the x power. Okay, well, we see this a value here is 3. That is the starting value. That is, if I substitute 0 for x, the output would be 3. Substituting 0, 2 times 0 is 1, 3 times 1 is 3. If I substitute 1, 2 to the first power is 2. 3 times 2 is 6. If I substitute 2 in place of x, well, 2 squared is 4. 4 times 3 is 12. If I substitute 3 in place of x, 2 to the third is 8. 8 times 3 is 24. Here's what you see. As x is increasing by 1, you will see that the y is doubling each time. 3 doubles times 2 to get to 6. 6 times 2 gets to 12, and 12 times 2 gets to 24. This multiplier is this value here. It is our growth rate. If this number is larger than 1, this thing is going to be increasing, and this amount here will be the multiplier from one term to the next if we're increasing by 1. So one of the key characteristics of our exponential function is the change over here is not a linear one. It's not an additive each time. It is some multiplier from one term to the next. All right. Now, if b is, this number over here should have been 1 if b is greater than 1. All right. Now, if b is less than 1, if this value b is less than 1 but greater than 0, if it's some number between 0 and 1, then we're going to have exponential decay. Then, also should have been then here. Then we have exponential decay. All right. Graphically, x and y axis. Graphically, we will have something that looks like this. Starts high and then goes down low. In this case, we're getting asymptotically close to the x-axis as we increase in the positive x direction, and it increases boundlessly and goes to infinity as we go in the negative x direction. An example of an exponential decay might be this: y is equal to 40 times 1/2 to the x power. Looking at a few values for this function. Again, this is my a. It is the initial value. That is, when x is 0, y is 40. Substituting 0 for x, 1/2 to the 0 is 1. 40 times that is 40. When x is 1, well, substituting 1, 1/2 to the first is 1/2. 40 times 1/2 is 20. Let's substitute 2. 1/2 squared is 1/4. 40 times 1/4 is 10. Substituting 3. 1/2 times 3 is 1/8. 40 times 1/8 is 5. This time you see these numbers are decreasing, much as you see this graph is moving downward as we move to the right. And here you'll notice that from 40 to 20, it's times 1/2. From 20 to 10, again times 1/2. From 10 to 5, times 1/2. So in this case, the multiplier is 1/2, thus the values are reducing. And you can see this multiplier is indeed this rate, as we said previously. So this value, b, will tell you the rate, that is the multiplier from one term to the other. This value a is the starting value. It is what 0 will pair with. Let's look at a couple of examples from our XYZ homework. Okay, question number 1. It gives us two functions. F of x is 4 to the x and g of x is 1/3 to the x. And it asks us to evaluate. So here we're just simply looking for some outputs. If the input is 0, what is the output? If the input is -3, what is the output? Well, MetaCalculator is really going to be able to help us with this. One thing I want to note are what these values are. This 4 and this 1/3, this is the b, the growth rate. In both of these cases, the initial value is 1. It's like a 1 multiplier out here, a 1 multiplier out here. So let's investigate MetaCalculator. I'm going to enter in the function 4 to the x power. 4 to the x power. Coming into my equations, instead of f of x, I'll type y equals 4, and then I use the exponent key x. Now what I see when I graph this is it's going to be increasing because my rate is greater than 1. Looking at the graph, and I see my graph is increasing. Okay, but all I'm looking for here are some function values. That is, looking at number 2, f of 0. What does 0 pair with? So going back to my table, whenever x is 0, y is 1. That's the starting value. All right, again, it's like there's a little 1 multiplier out here in front. So when x is 0, y is 1. All right, now I'm looking at my next f1, -3. I want to know what -3 pairs with. Well, if you substituted -3 in here, it would be 4 to the -3rd. That's like 1/4 to the 3rd. And I believe that's going to be 1/64th. Coming to my calculator, -3 pairs with 0.0156. That is 1/64. So back to here, f of -3 is 1/64. Okay, so you can continue in that fashion to answer all of these here in question 1. For this g of x, you would just input this exactly like you see it, 1/3 to the power of x. All right, I'm looking at number 4. It says y equals 1/4 to the power of negative x. One note that I want to talk about is if you are going to enter any kind of exponent that's not simply x, we need to group that in parentheses. If I were entering in y equals 1/4 to the negative x, I would enter it in this fashion. Y equals 1/4, I would group that in a parentheses just like they're showing it. But negative x, I want to group in a parentheses as well. Because I have two terms up there, it's essentially like -1 times x. And for both of those to be in the exponent, I need to group that into parentheses. And you'll see that this is an exponentially increasing because 1/4 to the negative x is the same as 4 to the positive x, because this essentially is 1/4 to the -1 taken to the x power. All right, I'm going to look at one more problem from the assignment. I'm going down and looking at problem number 14. It gives us this equation. Suppose you deposit $1,300 in an account with an annual interest rate of 8% compounded quarterly. Use the formula A equals P times 1 plus R to the n, then R divided by n to the power of nt. Well, this is an exponential because in our exponent we have our input variable. T is our input variable. We can see that right there, and there you can see that T is in the exponent. It says find an equation that gives the amount of the money in the account after T years. Well, they're giving us this A. P is the principal, 1,300. So here I'm going to enter 1,300. P is the principal, it's 1,300. Open parentheses. 1 plus R is my rate. All right. Well, our rate is 8%. I'll write that as a decimal, 0.08 divided by n is the compounding periods. This says quarterly. That means 4 times per year, thus n is 4. To the power of n times t, well, again, it's two things up there in that exponent. I need to group it in parentheses. N is still 4, and t is my input variable. I'm going to leave that as t. I've simply filled in all my blanks there. Preview to see if it's like I want it. And here you see we have the 4 to the t power. P is my 1,300, R is my 0.8, N is 4 because we're talking about quarterly. Okay. Find the amount in the account after n years. I'm just going to substitute 9 in place of n, but I'm going to type this in my meta calculator. All right. So we have y equals 1,300. That's my starting value. 1 plus 0.08 divided 4. That's my growth rate. That's the B. This is the A. This is the B. And my exponent here is 4. Instead of t, I need to use x in my meta calculator. I need to group this in parentheses, though. All right. And now I'm going to go straight to the table. Okay, the question is asking, find the amount of the money in the account after 9 years. So I'll just simply come to an x value of 9, and our output is 2,651.85. That is, if we invest $1,300, it's going to be worth twice as much, $2,651, if we're getting 8% compounded quarterly. That's a pretty high rate of return. So 2,651.85. 2,651.85. It says round to 2 decimal places. That's obvious in this case. We're just talking about money. All right. How many years will it take for the account to contain 2,600? Here we're looking for an x value. Well, I'm going to use my meta calculator to find that. Coming to my table. Here I see At 8, it's 24.49, and at 9, it's 26.51. So it's somewhere between 8 and 9. I'm going to use my calculator to get in closer to that. Here, I'm going to change my starting value to 8. And instead of counting by ones, I'm going to count by 0.05. All right. So now here you see we have 8 and 8.05 and 8.1, so forth. And I want to see, when does it get to be 2600? Here. At 8.75, it's 25.99, and at 8.8 is 26.10. So it's very close to this 8.75. That is an appropriate x value. So I just simply changed my start value, and my interval is the count, and I saw what value of x gave me the appropriate y. So 8.75. All right. D, if the interest were compounded continuously, how much money would be in the account after 9 years? Well, this one will be slightly different. If it says per period, like compounded quarterly or compounded monthly, we're going to use the formula we just saw. The amount is equal to the principal times 1 plus r over n time to the nt power. That is, this n is our number of compounding periods, this t is the time, r is the rate, the p is principal. If it says compounded continuously, we're going to use the same formula but make a little adjustment. A will equal this same principal, but we're going to replace this entire growth rate here with a special number. That special number is e. We're going to keep this t up here, but then we're going to use the rate as well. So this is going to be e to the power of r times t. This number e is a very important number in math. It's similar to pi in that it is an irrational number. That is, it's a non-repeating, non-terminating decimal. It is approximately 2.718, and this number goes on and on forever with no repeating pattern. It is called many things. It's called Euler's constant. It is the base of the natural logarithm, but in math, just to say e is enough that people know that it's this number, 2.718. It has a lot of usages, but one of the usages is this compounding interest formula. So in this particular instance, this is how we'll use it. A, our final amount, is going to equal P, our initial amount, which in this problem was 1,300, times this special number E, and E is this 2.718, but I'm going to write it as E. And then we want the power of R times T. In this case, our rate is 8%, 0.08, and our time T is 9. You can use the scientific calculator on your phone to evaluate this. I'm going to use our MetaCalculator scientific calculator. So back to the original screen, MetaCalculator. Instead of graphing calculator, although we could use our graphing calculator to find it, I'm going to go to scientific calculator. And I'm simply entering in 1,300 times, now I want that special number e, and any scientific calculator will have it. Here you see it, e to the power of x. And when we use e, we're almost always evaluating it to some power. So I'll click on that, and now it says exponent. That's what it means by it. It's now basically saying e to the power of, and now we're putting it to the power of 0.08 times our number of years. That's our rate times our time. All right, and it will evaluate that, and it is 2,670.76. So you see this value is slightly greater than that previous value because we're compounding continuously instead of quarterly. So that number will now go into that particular blank, 2,670.76. So you could enter that in, and that will be the answer to the final problem. With that information, you should be able to handle all the ones on 6.1.